So as Jen mentioned in his introduction, the University of Wyoming operates a research aircraft. This is one of 3 research aircraft that are funded by the National Science Foundation. The aircraft is pictured here on the left. It's a new research aircraft that just replaced a 50-year-old research aircraft that we had operated since the mid 1970s. And in addition to that research aircraft, the NSF NCAR Wyoming supercomputer also resides in southeast Wyoming, about 40 miles from the University of Wyoming campus. So we have unique access to that computer for running computer model simulations. We have roughly 1/7 of all the core hours from the NSF NCAR Wyoming supercomputer dedicated to the University of Wyoming. So it provides us a really unique opportunity to a lot of compute power. And I just want you to keep those 2 things in the back of your mind when we think about how are we going to maybe design a new set of experiments to explore cloud microphysics processes. I think I just need to click on this. Okay, so start at the beginning. How do we progress in our scientific understanding? And I've always liked this. I've always liked this diagram from this BAMS paper by Jeff Stith and a group of folks that talk about science in this the progression of scientific understanding in this sort of circular model, right? We start with some type of conceptual understanding, that is this model aspect of things that we may try to put into an actual numerical simulation of how we think something progresses. We run our numerical model, and that provides some type of output that we can compare to observations that we make as a way of validating the model. And we find that some model gets some things right, it gets some things wrong. So that forces us to rethink our scientific understanding, and we end up in this circular loop. And hopefully every time you go around, you gain a little bit better of an understanding. And the side to this is that, right, we're making predictions at the same time, and hopefully those predictions are somewhat benefiting society. So we're in this constant loop where we have to utilize models and observations constantly back and forth to improve our scientific understanding of what's going on. Another way to look at this is, okay, how do we bring all of these different observations together to feed into the numerical models, or these conceptual models and eventually numerical simulations? We need to be thinking about how do we collect observations, right? We collect observations in the laboratory. Maybe we collect observations from an aircraft or a mountaintop observatory, and maybe we have some remote observations. And all of these different observational strategies provide different information that feed back and forth between the observations and the model, and also between the observations and each other, right? So, for instance, an aircraft is able to observe cloud properties, not processes, but properties, which feed into a model, and then maybe are then again used to validate whether the numerical prediction of our model is correct or not. The same thing with laboratory observations. It observes actual processes, right? So you can actually observe a process happening in the lab, which can be used as a parameterization and numerical model, which makes predictions of the properties that we can validate with our airborne observations. So all of these things tie back in together. You can't just focus on one. to gain a larger holistic scientific understanding of the problem at hand. And our problem at hand is complex, okay? Right? So here we're thinking about mixed phase clouds and the processes that occur in mixed phase clouds, right? Where maybe you have liquid near the lower portion of the cloud, where the temperatures are greater than 0 degrees C, and you get water droplets that form, and they grow through coalescence and through condensation, and that's impacted by maybe the aerosol that are input initially into the cloud, and as we go higher up or colder temperatures in the cloud, we get the initial formation of ice, and that ice can then grow through various processes, and all of these things are happening in the cloud, and they depend on the location in the cloud, temperature, and some are time dependent, and there are a lot of different environmental constraints on all of these. And we can go through and we can measure the cloud. We can measure the cloud through an aircraft. If the cloud is sitting on a mountaintop, we can measure the cloud on the mountaintop. We can utilize remote sensing tools, and we can make measurements at different times in clouds and see how the properties change. And the change in the properties gives us some idea of the processes that are occurring, but it's not a direct measure of the processes, right? We're inferring something about the processes and their rates based on the change of the properties and times themselves. So the point that I want to make is that the observations that we have from natural clouds don't allow us to say something explicitly about process and process rates, but only allows us to infer something about the process and the process rates, which are so critical to numerical simulations. Okay, a numerical model, right? If we think of a relatively simple cloud model, okay, maybe we have 5 or 6 different types of hydrometeors in a typical microphysics scheme, and how we move back and forth between each of those hydrometeor classes, or how we let one hydrometeor class evolve. We have to account for all of the processes that are occurring, the microphysical processes that are occurring. And it's like, well, okay, we know, let's pick one. We know freezing. Okay, freezing is pretty simple, right? Water freezes. If it gets too cold, it turns to a solid. Shouldn't be that hard to figure out how you put this in a numerical simulation, but of course it is. We all know that, right? So freezing shows up 3 times on this diagram on the right-hand side. But the pathways through freezing are complex, right? Are we talking about primary nucleation, or are we talking about secondary nucleation? If we're talking about primary, are we talking about heterogeneous or homogeneous? If we're talking about heterogeneous, are we talking about deposition nucleation, immersion freezing? All of these things are, right, extremely complex. And all of them, if your model is all encompassing, has to include all of these things. So how do we do that? Well, we said very early on, right, that most of these process rates that we get in numerical models have come from laboratory studies, right? We look at one of these, we pick one of these things, and we go to a laboratory and we make measurements in a range of environmental conditions, and then we try to take that information and put it into a numerical simulation and say, okay, these are the constraints around here. Then maybe we can utilize aircraft observations to expand those constraints and say, it seems like when we're colder temperature, this or this environmental condition, maybe the rates slow down or speed up. We use some classical theories to also figure this out, but it's all very, very complex. And it's amazing the numerical models do as well as they do because they really represent this stuff pretty simplified view. Complex for sure, but when you get down to the nitty gritty, it's pretty simplified. Okay, so the point being that untangling these processes really requires some detailed understanding of the rates and the controls, the environmental controls of each process, to be able to represent them in numerical simulations. And laboratory studies, as great as they are, right, are often unable to test the full range of conditions. And right, that shouldn't be a surprise to us. But we do need to have a good understanding, right, of what these environmental constraints are and how the rates change as our environmental conditions or our environmental constraints change. Okay, we're not going to get there, but we want to be able to get closer. Okay, that's our goal. So preliminary, this may be a final conclusion now from a workshop that DOE held in the fall of 2023, about 2 years, which Daniel was also a part of, called New Directions in Atmospheric Ice Process Research. I want to highlight 2 bullet points that were part of this. And one is a grand challenge in atmospheric research is the understanding of ice processes within clouds. That shouldn't be a surprise. Ice is really hard. And this is spanning both primary and secondary ice formation. So thinking back to that freezing in our numerical simulation diagram, right? All of the different pathways to freezing. Overcoming longstanding barriers in ice process research demands a multifaceted approach to precisely quantify process rates and their environmental controls. Okay, so that's what we're going to focus on. But how do we do this? How do we accomplish this? So I'm going to start off with a bit of a story. Okay, this is the story of secondary ice production. Okay, and it started 50, 60 plus years ago. Okay, and the diagram that we're looking at on the lower right was published in a paper by Peter Hobbs back in 1980. Shows a function of ice, what he called ice enhancement ratio, as a function of cloud top temperature. This is saying if I have X number of INP at a certain temperature, okay, but I measure Y number of ice particles at that same temperature, Y being larger than X. What is my enhancement? How many more ice particles am I seeing than actually the number of INP that I have? And Peter showed that in clouds, especially in relatively warm clouds at temperatures greater than, let's say, -12 or -15 degrees Celsius, that the number of ice crystals far exceeded the number of particles that you would expect based on their best understanding of the number of IMP at that temperature range, like by orders of magnitude, right? So that had been known for a while in 1980. I mean, this was discovered in the 1960s, but this paper by Peter Hobbs and company really emphasized the point. And so during this period in the 1960s and 70s and 80s, people were looking at this idea of secondary ice production, the production of additional ice crystals that relied on the existence of ice particles already to produce or cascade, if you will, more and more ice crystals. And a paper by Hallett Mossop in 1974 in Nature, where they utilized a cloud chamber and a rime, what they call the rhyming rod. So they spun this rod around in a cloud chamber at temperatures in this -5 to -8 degrees temperature, -12 degree temperature range, and found that as this rod was collecting grime on it, it was also producing additional ice crystals in the cloud at the amount of on the order of something like 3 to 500 number of particles per milligram of ice rime that was building up. And that was like a eureka moment for the field at the time and for many, many years of, oh, okay, we're getting ice because we're rhyming these particles and they're producing ice splinters, and oh, all is good. We're happy. We can move on with our life now. Of course, there were very tight constraints on this, right? It was a really small temperature range. You needed the right size drops and on and on. But for decades, the secondary ice production freezing mechanisms that were utilized in numerical models largely only contain this so-called Hallett-Mossop process, also called the rime splintering process. Despite the fact that few laboratory or cloud chamber studies could really robustly reproduce the results from this 1974 study. People were trying and they couldn't do it. No one cared. It solved the problem, right? So it's like, people must be setting up their experiments wrong. There were other potential secondary ice production mechanisms, but that had already been introduced and explored even before Hallett-Mossop's experiment, but they were largely ignored because it seemed like the HM process could solve our problem that we were looking for, and there, during this period in the 80s and 90s, there was decreasing funding for lab studies, so there were fewer and fewer lab studies, and on top of it all, lab studies are hard, right? So let's go work on something easier. Okay. In the early 2000s, there was a renewed interest in secondary ice production, a number of experiments that were specifically set up to try to understand secondary ice production, and many of them were actually looking at Hallett-Mossop process and saying, okay, does this really explain it? Ice L, Ice T, Cope Med, the handful of other experiments that I know of that I was partially involved in, but many other experiments that I wasn't involved in, really started to critically look at secondary ice production, the Hallett-Mossop or rime splintering process, as well as other processes. A paper published by Paul Lawson in BAMS in 2023 looked at the growing top of cumuli as they penetrated through the -10, -12, -14 degrees sea level. And he was looking at warm-based cumuli. So these cumulus clouds that would form liquid drops, raindrops, low down in the cloud through warm processes, through collision coalescence. And then these drops would be lofted to higher locations in the cloud, and he was trying to determine, or he together with this group of investigators were trying to determine where ice formed and what processes might account for the formation of ice. And what they found was that the clouds, as long as you were in the middle of an updraft, the clouds would stay largely liquid, largely super cool to temperatures of about -10 to -12. And then between -12 and -14, they would glaciate very quickly. And so they were examining the particles that occurred during that time of glaciation. And what they found was they found a lot of things that looked like fragmented droplets that that when they froze, they shattered. Okay, and there had been this freezing fragmentation of drops, this idea of freezing fragmentation of drops for a very long time. This dated back to actually pre-rime splintering days, but hadn't really been investigated very much in laboratory studies. But they saw evidence of this, and at the same time, what they didn't find, at least in the updrafts, are evidence of any type of rime splintering process, because the temperature constraints, the environmental constraints that we believe we understand about rime splintering, they were outside of those. They were outside of those regions when they found ice. Okay, so that's the first question mark, or one of the question marks that comes up about rime splintering. A recent study, I think it was published just last year in ACP, by a group in, I'm trying to remember where Seidel's group is at. Are they in
Karlsruhe Institute of Technology?
Karlsruhe. Okay, I was trying to decide if they were there or ETH. And Karlsruhe set up a really nice study in a lab where they were able to suspend this ice particle in a flow of droplets that and very precisely control the temperature. So they have this suspended ice particle, a flow of droplets, super cool droplets passing it at -4 degrees, -5 degrees, -8 degrees, -10 degrees. Okay, so those droplets, obviously, when they impinge on this ice particle, they're going to rime onto this ice particle. So this is a classic idea, right, of being able to reproduce this idea of rime splintering, and they could control the size of the ice particle, the rimer, they could control the size of the droplets, and ideally, within certain temperature range, within a certain size range of droplets, they would be able to observe these ice splinters downstream of this rimer. The problem is they didn't find any, right? And they tested across the range of where we expect rime splintering to occur. And all of a sudden that, right, leaves everyone in the field, hopefully, right, scratching their head saying, what the heck's going on? Does rime splintering actually exist or not? Does it produce ice particles? And so they observed a little bit of production of ice particles, but very few, right? Hallett Mossa were like 3 to 500, and this is like 2 to 5. So, okay, so where are we at? Well, I'm going to tell you one more story, and this is of a project that occurred in Northeast US, Southeastern Canada a few years ago, called Wintry Mix, and we were utilizing the NRC conveyor. And I want you to focus on this panel on the very far right, outlined in blue, and this temperature profile here on the left-hand side. And we were passing through a cloud from top to bottom that had a cloud top of about -15 degrees Celsius. And at the base of the cloud, the temperature was about -5 degrees Celsius. Okay. And as we passed through, as we entered the top of the cloud, okay, we're looking here at images from an optical array probe. So just to give you an idea of scale, the vertical distance here is 1.3 millimeters. So the size of these little circles that we're seeing here are on the order of 100 or so microns. Okay, And the fact that they have holes in them is a result of the optics that occur at this size range with this probe. We don't need to talk about the details of that, but what I want to point out is these are all very spherical, and it turns out these are all liquid particles. These are all liquid drops that we're seeing up at the top of the cloud at minus 15 degrees Celsius. It turns out this is a really bad place to be in an airplane. Okay. So we have 100 micron droplets, and as we go down in the cloud, heck, by the time we get to minus 10 degrees, we have some 300 micron droplets at minus 10 degrees that are building up on the airframe and on the propellers and all of the stuff. And the pilots are going, we want to get out of here. And the scientists are going, no, we kind of want to stay here and measure this stuff. But then again, none of us want to die. As we get down to minus 8 degrees, we see 400 micron droplets. This cloud is devoid of ice. There's no ice in it, or there's very little ice in it. There's like less than 0.1 per liter of ice particles. Okay, so there's the occasional ice particle that's falling through the cloud, but there's very little. And then something really strange happens. We get to minus 6 degrees, and all of a sudden, our particles are mixed between, and I'm only showing the large particles here, okay? Because if I showed all of the particles, the cloud droplets, it would dominate the scene, and all you would see is cloud droplets, right? But we start to see this mix of large, super cool liquid droplets at minus 6 degrees and columnar ice. And as we get a little bit lower in the cloud to minus 5.2, we see nothing but columnar ice. Our cloud is glaciated. It went from a super cool cloud high up at cold temperatures to a completely glaciated cloud lower down at low temperatures in the exact same temperature range as we would expect Hallett Mossop to occur. What's going on? That's the end of the story. I don't know the answer to it, okay? I'm sorry to tell you this. But the story, right, what I want you to take away from this story is we have inconsistencies, right, with what we're seeing in some airborne observation studies, what we're seeing in some laboratory studies, and what we're seeing in other airborne observation studies. Okay, it's complex. We don't know.
So the red light, the sounding is taken from a different time?
Yeah, the red line was actually taken during the ascent through the cloud. So even though it's on this graph, this was an ascent through the cloud up to here, and then a descent through the cloud. So later on. So a triangular ascent, descent through the cloud. There's other things that are going on here, right? Because we see, again, we still see the same inverted structure, but we see different types of ice crystals here. I don't want to get into that. That's a whole nother topic and talk, okay? But it's very complicated, and it's a great question.
Okay. So you did see the same stuff, Jeff, on the ascent than you did on the descent, because it's not clear that you did. The glaciation.
We saw the same glaciation, but we saw different types of ice crystals.
The morphology is different, looks like.
The morphology is different. So
it could
the
be
cause of the glaciation may be different.
Or kinetic.
Or who knows?
They
Yeah.
have different temperatures during the ascent.
Yes. Yeah. Yes.
Yeah.
Yeah.
And my one thing is we don't know where that ice originated from. There's advection, right? So things are coming into the plane of your transect. So there may be an origin of ice that
There, yeah. So, like I said, this is a different talk, and I've given that talk before. We're working on the paper to sort that out. But everything that we've gotten to this point, and everything that we've looked at, basically said this is not being affected in. We're not in a different type of aerosol mass that's somehow coming in having very highly active aerosol that happen to be nucleating all of the particles here, whereas up here we have different aerosol loadings. We haven't seen any of that. Okay. But these are all great questions, right? Which are all good things that reviewers are going to be asking us as we put this paper together, which is why it's not been published yet.
The temperature range is consistent with HM stuff, so that looks really neat.
The temperature range is very.
Everything's
consistent.
kind of falling in that temperature range, and maybe it's just a question of semantics is what they're seeing.
Don't know. Don't know. Here's one more example from this case. Here we're looking at a vertically pointing Doppler radar. Okay, so we're looking at the velocity spectrum from a vertically pointing Doppler radar. Cloud top is up here around 5.5 kilometers. As we descend through the cloud, the particle fall speeds increase, consistent with what we would expect with growing drops through collision coalescence, until we get to this gray shaded region, okay, which is around 4 kilometers, around -8 degrees Celsius. And then we get a broadening of the Doppler spectrum, and we get a shift in the mean Doppler spectrum to smaller particle fall speeds, which is again consistent with glaciation, with freezing. And then we get a very consistent Doppler spectrum through the rest of the lower part of the cloud and the precipitation falling out of the base of the cloud of around 1 to 1.5 meters per second until it falls into this warmer layer near the surface and get melting. Okay. So let's get back to the question that I have at hand. Okay, how can we combine laboratory and cloud chamber studies and observational studies in the real atmosphere to improve our understanding of these processes? All of that was just trying to set things up. So observing and modeling how the clouds and precipitation respond to perturbations in otherwise natural clouds might be a way that we can investigate about factors that influence and or control different microphysical processes in a natural environment. I'm going to introduce briefly, hopefully, another experiment that we conducted in 2017 called the seeded and orographic wintertime clouds experiment, Snowy. This was a perturbation experiment. Okay. It was a cloud seeding experiment. So the idea was, hey, can we put silver iodide into a cloud, into an otherwise super cool cloud or mixed phase cloud, and convert some of the super cold liquid to ice that will then grow and fall out to the ground in the form of snow. Okay, we're trying to do snowfall augmentation with cloud seeding. But at the base, it's a perturbation experiment. We're putting something into a natural cloud and we're observing how that cloud changes. So the idea was we would release the silver iodide with an aircraft that was flying back and forth upwind. On the western side, the wind would push the material downwind to the east. And since the aircraft is releasing this stuff at discrete locations, if it works, if we are able to perturb the cloud in some observable fashion, it should show up as a zigzag pattern on the downwind side of the cloud. And we're flying back and forth with a research aircraft, we should be able to see very distinct characteristics of perturbations or higher reflectivities, right, where precipitation is forming downwind of the cloud. And lo and behold, on a handful of cases, we observed exactly that. Okay, so here are vertical cross sections through the cloud as we were flying back and forth along the wind of radar reflectivity. So the dotted line is the level of the research aircraft. So we're looking above and below the research aircraft. And we know where the silver iodide is being released, and we know when it's released, and we roughly know what the wind speed is. So we can predict roughly where the material should be at any given time as we pass back and forth. And lo and behold, we actually see these regions of high reflectivity that first form at the cloud top and then begin to extend to the surface. So as we fly back and forth in these, we're also able to measure the liquid water content and the ice water content and look at the individual particle imagery from that. And what we're able to see is that very early on, after the release of the particles, or below the level at which the initial nucleation takes place, our cloud is largely liquid droplets. And then we get ice crystals to form, which then grow principally, we believe, through deposition in this case. And as they fall, they can grow through aggregation and riming, etc. Okay. So a couple more examples. This work has all been published in the last 5 years or so, and we're still working on publishing data from other cases. Here's a case where we've actually induced the dynamic response in the cloud. So we released AGI at the very top of the cloud, and that nucleation of silver iodide and liquid droplets into ice particles has released enough latent heat to actually force an updraft and end up with a cloud top that sits higher than the otherwise surrounding cloud top. Okay, and we were able with the radar to measure the updraft in the cloud and show convergence and divergence around it. And at the same time, we can look at different locations in the cloud and look at the particles of the cloud and look at, again, the distribution between liquid and ice in the cloud. So it seems like, at least in this case, right, perturbation can be introduced into a cloud and can be observed in a very limited set of conditions. I want to tell you about one other project that's going on, and this is occurring in by a group at ETH Zurich. It was published initially by Jan Henenberger and company in BAMS in 2023, called Cloud Lab. And what they did in Cloud Lab is somewhat similar. They utilized silver iodide, just like we did in Snowy, but instead of doing this to try to measure if they could augment snowfall, what they did is they released it in a very benign in a very benign super cold liquid layer cloud, stratus cloud, and they made measurements of the cloud upwind of where they released it, and then they made measurements just a little bit of downwind of where they released the silver iodide. And they tried to infer, or they inferred something about the growth of the ice crystals, because they could see if there were any ice crystals upwind, and if so, how big they were. And downwind, they could measure directly the number of ice crystals and the size. So they could in some ways measure directly nucleation of these ice crystals and growth rates of these ice crystals. Okay. And they've now published results in a handful of journals. This is from a PNAS Nexus paper from last year that shows before seeding. This is droplet concentration in gray, and downwind of seeding. This is ice crystal concentration in blue, and we can see the downwind of the seeding. We have ice crystal concentrations on the order of thousands per liter in some cases. And they can also look at the sizes. They can look at ice water content, so they can begin to give measurements of conversion of liquid to ice mass. Okay, as well as this is a graph of major axis length of your ice crystals. So at different times, which at a given wind speed correspond to a different at different distances downwind, which at different wind speeds correspond to differing times downwind. They can make measurements of the major axis length of these ice crystals, and knowing that the ice crystals that have formed only after they introduce the seeding material, they can start to back out crystal growth rates in a real and natural cloud. Okay. So let's come back to our original question. What if we're going to think about utilizing perturbation studies, possibly, to be able to investigate processes, microphysical processes, what might that look like? And this is something that we've been thinking about at the University of Wyoming for a number of years now. We have an observatory that sits on top of a mountain that is isolated. It sits west of town, about 70 miles. And this mountain sits in a cap cloud about a third of the time in the winter. So basically sitting right on top of this mountain is this cap cloud that is generally mixed phase or super cool. Temperatures that range between -5 and -25 degrees Celsius. Okay. And also on top of that mountain, we have a large observatory that has largely been unused for the last 20 years. It was used a lot in the 1960s and 1970s for some of the early cloud seeding experiments, but it's gone largely unused after that. It sits in a pristine environment. It's in the middle of stinking southern Wyoming. There's nothing upwind of it for hundreds of miles. Okay. And so an idea is to go up and to measure directly ice crystals within the cloud, cloud characteristics, cloud properties, both within situ and on the ground and in situ with the aircraft, so we can measure on the upwind side and on the downwind side. This is an old idea. They were doing this in the 1960s with the aircraft that we had 3 aircraft ago. Okay. But what we have now is we have way better measurements. Okay. And that's what we found in Snowy. There was nothing special about the Snowy experiment when we went out and looked at cloud seeding, except that we had way better measurements than what was done in the 1960s and 1970s. So we can utilize our observatory, we can utilize our aircraft, and then at the same time, we can do high resolution modeling with the NCAR Wyoming supercomputer. So we have all of the things, if you will, that are needed to attack this problem. Okay. From a large conceptual standpoint. So I'm going to leave you with this last slide that basically shows cartoonish this idea, right? Yeah, you can utilize silver iodide, but theoretically you can utilize any aerosol. You can input any aerosol into the cloud. Or, right, you can just also, you're going to be observing natural conditions at the same time. You're making observations on top of the mountain, okay, in situ, and with remote sensing tools, and you're flying back and forth with the aircraft. And you're therefore exploring everything from the microphysical scale at microns, okay, or at least, millimeters to centimeters, up to kilometer scales, regional scales. Okay, and you bring the modeling into this. And of course, right, you upscale what you learn, so you can actually get even much larger scales than that. And I think that I'm out of time, and I'm happy to take questions.
Thank you, Jeff. Questions? No.
So do you have any thoughts regarding the picture you showed, the crystals changing from like super cold water then gradually to ice crystals?
Do I have any thoughts on what caused that? Well, when I saw it, I was sure it's Kalamasa. And that's because we made the measurements before Seidel's paper came out. And then after Seidel's paper came out, I've been scratching my head for the last few years. I still think it's halitosis because I can't come up with any other good explanation. But
Well, of course, I was also very intrigued, and maybe a comment or a question. You have this 400 micrometer droplets. This is huge. So is it this giant CCN? And the point, if you get so big, things freeze at very high temperature. And so I'm wondering, do you have measurements of the interstitial aerosol? As you get bigger and bigger, you scavenge more and more aerosol. So in a 400 micrometer aerosol, I can put 10 million aerosol particles in it. Then you have huge surface area. That's the reason why we can make ice cubes in our fridge.
yes,
And
yeah.
so I was just wondering, I know you this is beautiful. I have another question or comment, but if you would have in situ aerosol and the hydrometeors, and maybe you have scavenging as you come in, the coagulation gets faster and faster, small with big, or if they're the same type, you don't coagulate, scavenge so much. And so your scavenging efficiency goes through the roof as you get bigger and bigger. My question was, how does it start? Is this famous giant CCN you're looking for? Why do you have such big droplets?
Oh, I think you just have time
And
between the
then
cloud top
conversion.
and it's just collision
okay.
coalescence. There's nothing special about that because the droplets at cloud top are 100 microns, right? And if you look, so what I didn't show on here is if you look at the cloud droplet size distribution, as you go up through the cloud, it looks exactly what you would expect. It's low down in the cloud, it's 10 microns, then 20 microns, then 40 microns, then 50, and then 100 microns. And then what you also see then as you go back down through, right, that cloud droplet distribution shifts back to smaller sizes, but you have this drizzle mode that grows as you go back down through the cloud. So it's just straight collision coalescence.
Yes.
Now, a couple of your other questions. We don't have good interstitial aerosol, sadly, because everything was iced up.
Yeah.
Yes, we
I
measured
know
through
that's
that.
the problem.
And
You're in the bottom of the cloud, so you have also entrainment. So you have two things happening. You get a lot of fresh aerosol in, plus the big ones coming down.
yeah,
So anyway, it would be nice a mass balance. How much stuff is in there? So if you could collect this big droplet and then evaporate it to see what's in there, for example.
oh, if I was going to go back and make those measurements and I could find that cloud again, there's a million different things I would do.
It's so difficult,
but-
this measurement
yeah.
and this, I mean, so it's amazing.
It's a challenge though. I mean, I think all of your questions, right, are valid. What leads me to believe that it has to be secondary ice production involved somehow, whatever that looks like, is the very, very rapid glaciation over a very short period, right? So even if it's somehow kicked off by primary nucleation of maybe you are somehow getting enough aerosol into large enough drop that you're finally freezing the drop, okay? You're not going to glaciate the cloud that fast through primary nucleation alone. I don't think it's possible.
Well, maybe one last comment, because so many people asked this question, but the number of liquid droplets and subsequently the number of ice crystals look very similar, but that could be an artifact.
I think that's an artifact of how we did the plotting.
Okay, so I don't want to interpret.
Yeah.
Otherwise, you would say it's not a multiplication. If it's almost 1-to-1.
Yeah, no, and it's definitely not the case. I had some other slides that did show the size distributions and concentration.
Yeah. That's a tricky one.
Can you tell us more about the type of cloud? Is it like a stratiform cloud? Is it broken? Does it have side
That
effects?
particular cloud, it was a warm frontal cloud. Prefrontal cloud that was advecting from the south to the north, pre-surface warm front.
Do you measure turbulence, dynamics, anything?
It was actually a very smooth cloud. there was very little turbulence in that cloud. It's sad. I mean, the entire project, we're really interested in mostly what was going on below the cloud, because it was falling through a warm layer, and then there was a very small cold layer at the surface. And the main experiment was really interested in refreezing at the surface, or what was controlling the type of precipitation that fell at the surface. But this was an interesting case, because in the absence of all of that, right, even if it was cold at the surface, you might have been getting liquid at the surface, or you might have been getting ice at the surface because of what was actually going on in the cloud, not what was going on in the near surface conditions, depending on the thermodynamic profile.
Yeah, I was interested in cloud too. It's my experience, which involved actually sitting in a cold shed outside, taking measurements every 5 minutes with a microscope. It was amazing to me how rapidly the crystal habits and everything could change. And one thing we learned in impacts with flights is that, especially for pre-warm Raleigh conditions, is that you get ice generation aloft. Streamers, you would be all super cooled, and then all of a sudden, glaciated, within a minute and so forth. So what I'm really concerned about, our challenge in my view, is this Lagrangian, just this volumetric, how can we get a better handle on what's going on, three-dimensionally? Because things are coming out, from the side, hitting us, this way, and then, there's processes happening there that we can't observe, and then we all of a sudden get measurements of the crystals there, and then we're wondering where they came from, because we're always viewing it like a column model.
Yeah.
And so, I don't know how to deal, but I mean, given phase array radar volumes, I mean, we talked earlier, I mean, there may be ways we can somehow put this together, but.
I mean, that's the exact problem that we're working on right now. So we're trying to utilize, so we had at the same time, and I didn't show any data from that. We had 3 ground-based radars that were set up. We had 2 X-bands and the C-band radar that was set up in this area where we're making measurements. And so we have volume scans roughly every 8 minutes or so. And we're trying to utilize those volume scans through the depth to characterize the spatial homogeneity, heterogeneity in that area, to see is because I think we have multiple problems there, right? We have the potential for advection, right, which is a spatial heterogeneity, and we also have what could be temporal heterogeneities, right? And this, I believe, is probably happening, is that we're not seeing the same thing all of the time through the cloud, but these are really kind of episodic events. For whatever reason, something kicks it off, and you get this burst of secondary ice production in this area, and then it goes away. And this is the type of thing that you observe when you're on the ground. You go from freezing drizzle to ice all of a sudden for 2 minutes, and then you'll go back to freezing drizzle for the next 20 minutes. And it's really freaking hard to characterize and capture all of this with one airplane flying around and not knowing when or where this is going to happen.
Great. Okay, so I think we can continue discussing during lunch. Today we have lunch.
It's gonna be here, so we don't have to go very far.
Yeah, grab